Okay, I have a couple more. These are becoming more difficult.
That's not fair.
I know. I made these and I still find them very difficult. So this one, is it the letter S, the letter B, or W? Let me show you again. S, B, or W? Okay, who is for S? B, W, it's B. So it's getting harder. It's getting harder. The next one is the hardest. It's also the last one, so you'll be saved. This one is not anymore even just purely white. This is a grayscale image. And which one is it? Which emoji is it? Let me show you again. A, B, C. Okay, C it is. And this time it's really a grayscale image, as you can see. Okay, so whatever our algorithm is doing, it needs to be able to know all of those tests perfectly, and not out of 3 choices. It has to reconstruct the actual image, even if it's a grayscale image, not only a black and white thing. So that's to give you the idea of the difficulty of this inverse problem. So now let me explain you how this reconstruction works. So remember, this was our case of 2 disks. This is the data, so what should we do with the data? What should the computer do mathematically to this data to find out what was it? The first trick is the so-called back projection operator. Given one direction and one profile, we are sending the data back into the image along the X-rays that produced it. And the intensity along each ray comes from the profile. So here zeros, here zeros, here zeros, and this profile we are sending in along the lines. And we can do this along many directions. But this is not the only thing. We have to sum them up. We have to sum these images. So if we sum the images, already magically, you can kind of see the disks. They are appearing. Of course, there is some kind of weird stuff around them, but you can see the disks already, although blurry. Now, of course, I only showed 7 directions. We can use all the directions. In case we measured from all directions, we can just integrate over the circle and sum up all of them. So now we are using the first trick, the back projection. We can see our object, but in a blurry way. Something is still missing. The method is called filtered back projection. So what is missing is the filter. For the filter, I'm using something I call multiplication by the ice cream cone, which I'm afraid this is a very technical step. We are following the famous French professor Joseph Fourier, who defined a so-called Fourier transform that takes any image into a so-called frequency domain. In the frequency domain, which is totally unintuitive for a person, we make the high frequencies stronger, so low frequencies in the middle, and the more you go away, it's a higher frequency. We make them stronger by multiplying by this, what I call the ice cream cone, and then we make the inverse transform. There's a mathematical proof published already in 1917 by Johann Radon that we get perfectly the image back by using this operation. Just to give you an intuitive idea of what is going on here, let me refer to this picture of myself in my favorite shop at the airport of Tokyo in Narita. It's a Hello Kitty shop, and if I apply the same filter to this image, you see that it will enhance boundaries, edges. So it's kind of an edge enhancement, taking away all blurring. So, That's what's happening here. The projection data is sent back into the image, and a filter is applied. That's how it works in these classical, traditional X-ray devices. Then actually, I would like to take you to a newer territory. Somehow the classical tomography is well understood. It's really used every day in hospitals. It was invented already in the 70s. Of course, it's made better and more effective, but still it's kind of well known when you have very comprehensive data from all directions. Sometimes you cannot have it. Let me describe you a project I worked on in my time in the industry. So if a person is missing teeth, I'm sorry for this image, I made it black and white, so it's not as gross as the original, but just to give you an idea what can be done today if teeth are missing. The idea is to fix this kind of titanium screws and then attach dental implants to those. So how to put these in place of the missing tooth, the dentist needs to drill a hole. So here is a cross-section of that area. So the dentist needs to drill a hole where the screw is attached, but there is a danger here. Inside the jawbone of all of us, there is going a tunnel containing nerves. You can see the tunnel also here. If the dentist drills too deep, the nerve will be damaged, and it results in chronic pain, maybe partial paralysis of the face, maybe an expensive lawsuit for the dentist. So the drilling has to be done as deep as possible to make it sturdy, but not too deep. So how many millimeters is it safe to measure? In the old days, these kind of things were measured in such a way, so this is 100 years ago, the patient had to hold a film holder covered by phosphorus inside, resulting in a set of images that had to be arranged on a light table. So this professor of University of Helsinki, Yrjö Paatero, was responsible for dental imaging at University of Helsinki in the 40s, and he got really fed up with this, playing around with these little X-ray images, and started thinking, could we perhaps take an overall image of all dental structures with one sweep, with some kind of a machine? So this is from his patent. This is the first generation machine, and in these days the machines work like this. You enter the panoramic device, it will rotate around the head, and it will collect this kind of an image. You can see all the dental structures there. Actually, although personally I'm not a boxer or hockey player, still I'm missing a tooth as well. It just suddenly broke and had to be removed, although I said, I mean, come on, it was my favorite tooth, but she took it away. So there it is. So if I ever would go for the implant, you could kind of see, so here is the nerve channel going here, you can see very vaguely, here is the bottom, where I can't really see where is the top. So actually, it's not safe to use this, although this is a very useful image for many purposes. It's not safe for measuring those millimeters because there is geometric distortion in this image. It's a very strange image. It's based on a very ingenious movement, picking out a sharp layer inside the dental arc. But, for example, horizontally it has parallel beam geometry, and vertically it has fan beam geometry. So it's a really, really weird image, actually. So this is not good for the measurement. But at my company time, we started thinking, could we make this machine work in a different way? Could we use this machine to do slice imaging? We faced a couple of problems. One problem was that the camera inside the machine is a narrow one, like this. It has 64 pixels width and 2,000 pixels high, because that's fine for this kind of images. But we would need really X-ray photos. Also, the machine cannot move in arbitrary ways, only in some ways. So what we did, we reprogrammed the machine so that it collects pictures by a scanning movement like this. We couldn't do this all around, though. We could only move the machine in such scanning way in an opening angle of 40 degrees. So this is kind of the situation. We can collect this kind of images from different directions, but only from this 40-degree angle of view, which makes the mathematical slice imaging problem much, much harder, and we cannot anymore use this filtered back projection trick, because for that we should go all around and measure at many more, much smaller angular steps than this one. So we had to develop some new methods for this case. So we actually divided the unknown area into 7 million little voxels. Then we had to find out what is the tissue inside each voxel, and our data was 11 images, 1 megapixel each. I will explain a bit more about the math in a minute. Let me just first say how this approach works. The other option for dentists is to use so-called cone beam CT. That's a dedicated dental machine that goes all around the head and picks out very many images, and it uses filtered back projection type method and produces a really, really perfect high-resolution volume that can be sliced and cut in any way. So here you can see the nerve channel, and the measurement should be from here to here. Our method, in contrast, uses the machine that the dentist already has, so the clinic doesn't have to invest in a new device, it's already there. We just provide a mathematical software update so that it makes this image. This is not perfect at all. We have many errors here, we have ringing artifacts, many things are wrong, but slicing in exactly this important way will give good information about the location of the nerve channel and where is the top ridge here. Much of anything else is kind of poorly reconstructed, but because of the directions of imaging and the geometry, we can get this piece of information reliably. And also the patient will receive only 1% of the radiation dose compared to this technique. So this was kind of an idea of using mathematics in the service of life. Instead of thinking, how should we measure to get the most perfect reconstruction? We asked, what is the least amount of radiation we need to give to the patient so that we still get this one piece of information out? So that's what we did. It was quite a project. We worked on it, I think, 6 or 7 years first, very intensively with 3 different projects funded by the Finnish government technology project funding agency. As you can see, there were a lot of people involved, engineers, dentists, mathematicians, physicists, computer scientists. We worked under several companies. So it was quite a big project, but eventually we got it to work. But so, like I mentioned, this way of imaging cannot be done with this filtered back projection method I explained to you. There needs to be another method. I want to give you a little idea how do we approach this problem. First of all, well, this is my lab at the University of Helsinki. Zenit, my former Indonesian student, defended her thesis in May this year. She's now at Aalto University continuing her tomographic work. This is Alexander Meany, my current PhD student who actually built this laboratory that we used for measurements. So one data set we took was just of a walnut. If you are interested in playing around with the data, it's openly available online. What we did, we imaged this walnut from 1,200 directions. And if you use all of these 1,200 directions with very small angular step and you use filtered back projection, you get a very detailed image. You can see these sub-millimeter, I think this is like 1/10 of a millimeter, something like this. You can see very fine details. But then if you think of sparing the walnut of too much radiation and take only 20 images and use the same algorithm, filtered back projection, this is what you get. The algorithm is not at all designed for this kind of sparse data, so it's no wonder it's not as good. And now in the field of inverse problems in mathematics, we look for methods that could could use different kinds of extra information, a priori information, on top of the measurement. So this is one example. This is called total variation regularization. These two images have been computed from exactly the same data. We just use a different assumption what kind of an object there is. And there is a whole family of methods. This is a hard wavelet sparsity. This we saw already, it's a total variation. This is a Dobeschi 2 wavelet sparsity. This is based on total generalized variation developed by Austrian researchers. And so you can see that using different a priori information from the same data, we get very different images. And the trick is to have good, proper extra information to compensate for the missing data. And then a few words about the mathematics in this kind of sparse data imaging. The inverse problem we write in the way that we think that our target is divided into pixels or voxels. Pixels in this case. So here we have a square-shaped patient that has 9 internal organs, all square-shaped as well. And after calibration, our readings at our X-ray detector can be interpreted as, if we think that the length inside this small square is 1, so we have 1 times 4 plus 1 times 4 plus 1 times 5. So we can interpret these numbers as row sums of this array of attenuation values. Then we rotate our device. We get column sums of the same numbers, and if we rotate at an angle, we need to remember the teachings of the great Pythagoras from ancient Greece and remember that the length of this diagonal here is square root of 2. That's why square root of 2's appear here. So this is the so-called direct problem of tomography. If we know the numbers inside, it's a quite easy task to compute what measurements would we get. The more interesting problem is this one. This is tomography in the way we look at it in the sparse data case. It's a bit like a Sudoku problem. Find the right numbers in the array that match the measurements from different directions. But then there are difficulties. For example, like you saw in this dental imaging case, we could not image from all around. We were limited in the range of views, a little bit like here. We can only see the horizontal and these 45-degree images. Already there we face some mathematical problems. We are trying to find 9 numbers out of 6 equations, which is impossible and shows up as non-uniqueness in the inverse problem. For example, here are 3 patients that give exactly the same data in these 2 directions of X-rays. So how do we know which one it is? This is the problem we faced, although at a much larger scale in the dental imaging problem, how to choose. So we need to teach the computer some systematic way of choosing among all these candidates. One simple thing is non-negativity constraint. We cannot have negative numbers because physics tells us that this means that inside this square the X-ray would get stronger instead of getting weaker. And this is not possible by physics, unless there is something radioactive inside the patient. But even then, it would be weird. So we can rule this out. But then choosing among these ones, the thing is we have to find a mathematical formula that favors among all the possibilities those ones that most look like dental tissue. That's what we wrote down in the computer and made it work that way. Okay. In the end, I would like to close with really a mathematical view of this, because you know mathematics is general. Mathematics appears in so many different places. So tomography is not only about X-rays. Also visible light brings us some tomographic problems. In this case, it's about telescopes. So for example, like this one in Chile, because the atmosphere is always a little bit turbulent, the images are a bit blurred and changing in time. So how to sharpen them is they actually have a mirror that can be deformed by thousands of little actuators that change the shape of the mirror. And the changing of the mirror has to be done like 1,000 times a second to follow the movements of the atmosphere. These lasers are artificial guide stars shot up there that can be used for calibrating the movement of the atmosphere, and then the mirror, there's a tomographic problem to be solved and how to move the mirror then to sharpen the images. And this is also a limited angle tomography. Here the angle of view is, unlike the 40 degrees we had, here is 0.1 degrees. Another visible light problem is this Envisat satellite that for many years measured the ozone layer in space. What it did, it looked at some star, and when the satellite is going around the Earth, the star is setting down behind the horizon, and the satellite could measure how strongly different colors of light were attenuated when they travel through the atmosphere. And this tells about the ozone content, but also this is a so-called exterior tomography problem because there's no data through the Earth, only through this atmosphere, so they would only have these line integrals outside the Earth. But it can be used for recovering the profile, the amount of ozone at different heights and all around the Earth. As a quite funny application of tomographic projection imaging, some researchers found that there's an extra new secret chamber inside the Cheops pyramid. They found it by using cosmic muon particles that come from the outer space and go through the pyramid. So I'm waiting to see when they do it tomographically from different directions. This is a nice physical example as well. For X-rays, this coffee making would look very different because aluminum would attenuate X-rays more than water. But for neutrons, this is imaged with neutrons. Water will very easily capture neutrons in the hydrogen atoms, so water is almost opaque for neutrons, but metal is kind of transparent. So also tomography can be used in very different physical situations where the probing energy can be very different from X-rays. And as my last example, I return to biology, the theme of the day. In this wonderful study, the researchers used first cryo-freezing of these little bacteria and then electron microscopy. From different directions, they used electron beams to probe a bacterium, and they could recover the structure of the swimming engine of the bacterium. It looks like this. It has largely the same components than human-made electric motors, but you know, this is a very small one. It's just a part of a bacteria. So tomography opens up so many different possibilities. It's really an amazing field and a mix of mathematics and many other fields. At this point, I would also point out if you like this kind of stuff, you can check out my YouTube channel where I publish popular science videos. It's a good way to learn Finnish as well. So far they are mostly in Finnish. Most of them have English subtitles though. And that's all I had to say. Thank you very much.
Thank you very much, Samuli. It was really interesting to know, and I will polish my Finnish. Kiitos, kiitos. So we have some time for some questions, and I promised also that if there is someone who is more, would like to use the Swedish, Samuli is very fluent in Swedish as well. He's studied Swedish in school, I guess. Yeah. So you can ask the question in Swedish, and I can at least translate it. So that's a general thing. But so an English question, yes, please. But we have to wait for the mic.
How much, because you often measure discretely, right?
Yes.
So what progress is there?
Sorry?
I mean, because you cannot measure in a continuum fashion.
True, yes.
Right? So and you may speed up things, for instance, when you have certain symmetries or something. Is that possible to then do it quicker?
Sometimes it is, but usually we don't assume anything like that because we want to kind of give the most freedom to the object, try not to know something about the object that we don't. And sometimes the geometry is also not completely symmetrical and cannot be controlled so well. So usually we just try to model the geometry of the measurement as accurately as possible and then just use a general method. I think these days computers are so fast that we can move on without such assumptions.
Thank you. Any other question? In any language? Jake. This will be a smooth transition.
Oh yeah, I'll just take the microphone up. Thanks for that. That was really interesting. It's fun, especially someone who uses those images quite a bit medically, to see some of the maths that I think about. So when it comes to like the very last slide, I'm curious about the microcryotomography.
Yes.
So sensor-wise, I mean, how small is the sensor, and what are you using there?
Yes, I must say my understanding of electron microscopy is limited, but I think they scan over. I think they have an electron beam and they move the beam in a scanning way along the domain of the sample. I think, I'm not 100% sure about that. Then they have to rotate the sample for sure, yes, they do. Sometimes, at least for some molecules, I know when they know they have the same molecule there in random positions, sometimes it's possible to use an algorithm to recover the direction through or find the random projection for each sample and then that way construct a data set. With this bacteria thing, I should check this one if they really turn and move it or if they have plenty of the same kind of bacteria. I would think they turn it, but I need to check that.
Thank you. Thank you for that. And I guess no further questions. So we move on to the next.
Yep.